In this video, we're going to talk about suggested homework problems from 9.6. We'll be talking about the ratio and root tests. These are very important going forward with our next sections in 9.7 and 9.8, 9.9, 9.10. Just going forward here with the rest of chapter 9, we'll be using the ratio test especially a lot. So pay close attention to this. So what can we conclude about the convergence or divergence of the series AN if we know that the ratio of the n plus 1th term to the nth term, the absolute value of that is equal to 0. For number 1, we can say that it converges, and I would say absolutely here, because I don't know if this is a alternating sequence here, but because it involves absolute value bars, it tells me that it's absolutely convergent, not conditionally convergent. So 3, if it equals 3/2, we're comparing this to the idea of the R in a geometric series, that if it's between 0 and 1, that it's going to be convergent. It can include 0 because if I add up all zeros, then it'll be 0, which is convergent. If it is 3/2 here, then that R value that we get from taking the ratio of the last terms there, being the absolute value of it being 3/2, that's going to be divergent. If it's equal to 1, like in problem number 2, that doesn't tell us anything. That's inconclusive. And the same thing for the root test, has the same conditions. So if the root test here, the nth root test, comes out to be greater than 1, it's divergent. If it's less than 1, it's convergent. If it's equal to 1, it's inconclusive. So you could probably do all 6 of those pretty easily. Let's go ahead and look at number 7. This test in particular for ratio test is great to use when I have exponentials, factorials, or a mixture of both. So let's establish that 9n plus 1 over n minus 1 factorial over 9 to the n times n minus 2 factorial, where this was my series right here, 9 to the n times n minus 2 factorial. What's that going to do? Well, this is 9 to the n times 9, and this is times n minus 1 times n minus 2 factorial. So this is going to be 9 to the n and 9 and n minus 2 factorial. Those will cancel and leave me with 9 times n minus 1, which is exactly what the right-hand side says it should be. So that's good. Let's look at number 11. And we want to match the series with the graph of the sequence of partial sums. So 11 says summation n equals 1 to infinity, negative 3 to the n plus 1 over n factorial. So this is A1 would be 9 over 1 is 9. A2, I'm going to be taking 9 minus 27 over 2, which is negative 9 over 2. See if we're starting to see one that looks right, that starts off with 9 and then negative 9/2, and then this is going to come back and be positive negative. So already I can tell, because it's alternating, that that one has to be F. I don't have to look any further. There is only one of them that was 9 and then negative 9/2 and would be alternating back and forth like that. I wanted to find, this would be S, not A, S1 and S2. I wanted to find S3. That would be negative 9/2 plus, and then this would be 81 over 6, which would be a negative 27 plus 81 over 6 would be 54 over 6 would be 9 again. So there it is back up there, and we'll just keep going back and forth. Let's look at number 13. And 13 is part of the same matching group. It says summation from n equals 1 to infinity for n over 5n minus 3 to the n. S1 would be 4 over 2 is 2 to the first is 2. S2 is 2 plus, then 8 over 10 minus 3 is 7. Squared is 64 over 49. 49 times 2 is 98. Over 49 is 12. 162 over 49. This is a number that is a little bit bigger than 3, I think. 162 divided by 49, that's 3.3061. So let's look and see. This is growing, starting at 2 and going up. None of the other ones are going up that fast. They don't start at 2. This one doesn't start at 2. This one starts at 4. So the only one that this can possibly be here is A. I don't need to go very far to find out which one it is with matching. Let's go ahead and look at number 21. My instructions here tell me to use the ratio test to test for convergence. If the ratio test is inconclusive, determine the convergence or divergence of the series with other methods. So 21 says summation n equals 0 to infinity, n plus 2, and then 9 over 7 to the n plus 1. And so I'm going to have limit as n goes to infinity of the absolute value of, add 1 to all of the n's here, n plus 3 times 9/7 to the n plus 2. It's the reciprocal here, so n plus 2 goes in the denominator. 9/7 n plus 1, 1 over. So this is going to be limit as n goes to infinity of n plus 3 over n plus 2 times the absolute value of 9/7 to the n plus 2 minus n minus 1. The n's will zero each other out. So this is going to be absolute value of 9/7. Limit as n goes to infinity of absolute value n plus 3 over n plus 2. This is 9/7 times 1 is 9/7, which is greater than 1. So this diverges. Let's look at 25. Summation n equals 1 to infinity, n cubed over 3 to the n. I may have said this already, but what we start at doesn't really matter because we're only looking as we go way out to infinity what the last couple terms are here. So hopefully you caught on to that I really don't care about whether this starts at 0 or 1 or whatever. N plus 1 cubed over 3 to the n plus 1 times the reciprocal of this, 3 to the n over n cubed. And this is going to give me 3 in the bottom, so I'll pull a 1/3 out. Limit as n goes to infinity of n cubed plus 3n squared plus 3n plus 1 over n cubed will be 1/3 limit as n goes to infinity, 1 plus 3 over n plus 3 over n squared plus 1 over n cubed. All these are going to 0. Is 1/3 times 1 is 1/3, which is less than 1. So this converges. Let's look at 31. Summation n equals 0 to infinity of e to the n over n factorial. So this will be limit as n goes to infinity, e to the n plus 1 over n plus 1 factorial times n factorial over e to the n. Put this in absolute value bars. This will become e. This will become n plus 1. So this is e. Limit as n goes to infinity, 1 over n plus 1 is e times 0 is 0, which is less than 1. So this converges. Let's look at 35. Summation from n equals 0 to infinity, 5 to the n over 2 to the n plus 1. And we'll make this limit as n goes to infinity, 5 to the n plus 1 over 2 to the n plus 1 plus 1 times 2 to the n plus 1 over 5 to the n. And this is pretty easy that this is going to be 5 here. This is 5, limit as n goes to infinity, absolute value 2 to the n plus 1 over 2 to the n plus 1 plus 1. I'm going to multiply by 2 to the negative n over 2 to the negative n is going to be 5, limit as n goes to infinity. This is 1 plus 2 to the negative n over 2 plus 2 to the negative n, 5 times 1 plus 0 over 2 plus 0 is 5 times 1/2 is 5/2, which is going to be greater than 1. So this diverges. Let's look at 41. Summation n equals 1 to infinity of 3n plus 2 over n plus 3 to the n. This is a great time to use the nth root test because this is a function of n to the nth power. So limit as n goes to infinity of the nth root of 3n plus 2 over n plus 3 to the nth power will be limit as n goes to infinity of 3n plus 2 over n plus 3 is equal to 3 is greater than 1, so this diverges. Let's look at 47. 47 also wants me to use the nth root test. Summation n equals 1 to infinity, n over 3 to the n. Now I'm going to tell you that if you didn't see this in the notes or earlier in the book, that we proved a while ago that equals 1. We're going to need that in this problem. So limit as n goes to infinity of the nth root of n over 3 to the n is limit as n goes to infinity of the nth root of n over 3 is 1/3, which is less than 1. So this converges. Let's look at 51. Summation n equals 2 to infinity, n over ln of n raised to the n. Take the limit as n goes to infinity of the nth root of n over ln of n raised to the n will be equal to the limit as n goes to infinity of the nth root of n over ln of n is 1 over infinity goes to 0, which is less than 1, so this converges. Let's look at 57. So 57 says summation n equals 1 to infinity, 5n over 2n minus 1. And this is just review, so use any appropriate test. Limit as n goes to infinity, 5n over 2n minus 1 equals 5/2. It's not equal to 0, so it diverges by the nth term test. Let's look at 61. So summation n equals 1 to infinity, 10n plus 3 over n and 2 to the n. So I'm going to, before I do anything else, make this 10 plus 3n to the negative first over 2 to the n. And then I'm going to look at this one with the nth term test. It would go to 0, so that's not helpful. Let's go ahead and do a comparison test here. So so this is my an is equal to 10 n plus 3 over n 2 to the n, and make my bn equal to 10 n over n 2 to the n, and the n's will cancel. So this is 10 over 2 to the n, or 10 times 1/2 to the n, which looks like a convergent geometric series to me. So I think this is has the potential to converge. So I'm going to use my limit comparison test here. Limit as n goes to infinity of an, which is 10n plus 3 over n times 2 to the n, over, let's just multiply by the reciprocal. So 10 n plus 3 over n 2 to the n times the reciprocal here, 2 to the n over 10. The 2 to the n's will cancel, and this will be limit as n goes to infinity of 10n plus 3 over 10n is going to be equal to 1, which is what I want. That's positive. So an series and bn series both converge or both diverge. The series of bn converges by the geometric series test. So series for an also converges by the limit comparison test. All right. Now at number 65. 65 says summation n equals 1 to infinity n factorial over n times 7 to the n. And I see a combination of factorials and exponentials, so I'm going to try my ratio test here. Limit as n goes to infinity of n plus 1 factorial over n plus 1 times 7 to the n plus 1 times n times 7 to the n over n factorial. So this makes n factorial here, which cancels out with this. And this makes a 7. And this is limit as n goes to infinity of n over 7, which is going to go to infinity. So this diverges by the ratio test. Let's look at 67. It says summation n equals 1 to infinity of -1 to the n, 3 to the n minus 1 over n factorial. And this is alternating. So if we use the ratio test here, which I think we will, and we get an answer, we need to say that it's absolutely convergent. So limit as n goes to infinity of and forget about the sign changer, absolute value of 3 to the n plus 1 minus 1 over n plus 1 factorial times n factorial over 3 to the n minus 1. And so this is limit as n goes to infinity of 3 to the n minus n plus 1. When I bring this up and subtract, over n plus 1 times n factorial, and the n factorial cancel. So this is 3 to the first is 3, limit as n goes to infinity, absolute value 1 over n plus 1 is equal to 0, which is less than 1, so it converges absolutely, or is absolutely convergent by the ratio test. And let's wrap up with 91, which is going to kind of show us where we're going to be using this going forward. But I'm going to have this thing called a power series, which is going to have x to a power of n like this. And I want to see for what values of x this will converge. And because it's got the n factorial in it, I'm going to use the ratio test. Sometimes I'll want to use the root test instead, but especially when I see factorials, I want the ratio test. So n plus 1 factorial x over 2 to the n plus 1 divided by n factorial x over 2 to the n. And I need this to be less than 1 to have convergence. So limit as n goes to infinity of absolute value of, that'll be n plus 1 in the numerator, and this will be x over 2 to the first, needs to be less than 1. So, I have an issue where I have infinity times something and I need it to be less than 1. So the only way that's going to happen is if this something with an x here is equal to 0, because the only way that I get something times a really big number to be less than 1 is if this really, is if this other number is 0, because 0 times anything is 0. So x has to be equal to 0. This is what we call pointwise convergent, or it only converges at a single point. Every power series is going to be convergent when this argument inside of the nth power here is equal to 0. That's kind of the trivial case here, but we would hope that it would come up with additional answers, maybe a whole interval of answers is what we're looking for usually. Sometimes an open interval, sometimes a half open interval, sometimes a closed interval, where we would be convergent occasionally. This whole thing over here, this expression with n, goes to 0 apart from this, and it doesn't matter what this part with the x does, it's always going to be 0, and it's going to be convergent everywhere. And we love that. We love these power functions that are convergent everywhere, and we'll know why when we talk about power series more and Taylor polynomials and Maclaurin polynomials when we keep going in this chapter. So power series, super important to calculus, and this idea of we've taken curves and we've done linearization with the tangent line, where we say, okay, this tangent line is a good approximation right there at that point at C, it's exactly equal to, and I can stay close to it with that first degree polynomial. The first derivative will agree. But what if I wanted to make a polynomial that traced the curve a whole lot better and agreed all around C, not just at the first derivative, but the second derivative, the third derivative, the fourth derivative, all the way out to the nth derivative. And you just really couldn't tell any difference between that crazy function like sine, cosine, e to the x, ln of x, something like that, and this polynomial function that estimated it within that good interval. It traces it pretty much exactly, and all of the derivatives are the same too, for depending on what degree of polynomial I use there. Well, that's what we're going to learn how to do. That's really all the calculator does as well. If you think the calculator is really smart and knows how to do sine and cosine and tangent and log and natural log and e to the x and all these other buttons that are on your calculator, it's really just doing this idea of something called a power series, and it's really just making a polynomial that traces out almost the exact value, everywhere to a really close level of precision where it agrees with the value, it agrees with the all the derivatives and so on, over this interval of convergence. And so that's what we're going to be looking at going forward here. And these ratio test and root test, especially the ratio test, is going to be necessary for us to figure out this idea of the interval of convergence, the radius of convergence, and so on. So more on that as we go forward. Hopefully that whets your appetite a little bit, and you say, that sounds really interesting. I'd like to know more about that, about how I can make polynomials that estimate transcendental functions, like sine, cosine, e to the x, and so on. So we'll get into that in the next video, I believe, when we come back and talk about 9.7. So see you for the next video.